Pick up our conversation here with density. I think we saw this slide. The other important thing about the density is the density of water, and density of liquid water, again, in any type of book problem that you may come across or need to use the value for water. Usually 1 gram per milliliter is the value that you should use. And that's another one of those figures that you do need to know, just sort of know. As we talked about, density does change with temperature. So technically speaking, if the temperature is really not like 20 degrees or 25 degrees, the density really won't be 1. But pretty much 99% of the time, if you find yourself in a problem that you're doing and you somehow need to incorporate the density of liquid water, that 1 gram per milliliter is definitely the value that you should use. Density has a formula which is mass divided by volume, and it has certain units, and most of the time the units of density are grams per milliliter, are grams per cubic centimeter, which is typically what we use for solids and liquids. We don't deal too much with it in this particular class, but in the next class that you take, usually the density example are given in grams per liter, the typical density units that you associate with gases. For us in here, probably grams per milliliter, grams per cubic centimeter is definitely in the 2 units that you will see. The number always stays with the grams part, and it's always like 1 milliliter, 1 cubic centimeter sort of on the bottom. Also a reminder, right, a milliliter is basically a 1-to-1 conversion between that and a cubic centimeter. Obviously, those are 2 different ways to get volumes. We can take the volume by simply just reading the volume, or we could do something like you did last week by taking some length measurements of like the square or the wood block, the length times the width times the height, which will give you your volume in cubic centimeters when you cube that. We also need to know how to properly rearrange this, right? So density is mass divided by volume. We times the volume to each side and divide by the density. Volume is mass divided by density. Our mass is volume times density. Sometimes people like to remember everybody's favorite place, the DMV, right? Triangle. So density is mass over volume. Volume is mass over density. And mass is density times volume. It's just a quick way to remember it. We will, in a lot of cases, has to be, or you will be able to sort of solve for any of those sort of variables there: volume, density, or mass. Any questions on that there? All right, so let's take a look at an example here. So let's grab a calculator and we'll knock this one out here. A block has a volume of 25.3 cubic centimeters. It has a mass of 21.7 grams. What is the density of that block? Okay, so since obviously we're dealing with density, that would be a good place to start. We have a volume given to us of 25.3 cubic centimeters. We do have the mass, which is 21.7 grams. So clearly, if we just kind of check off what we got, density seems like a pretty good thing to solve for. We're ready to put it just directly in here. So 21.7 grams divided by 25.3 cubic centimeters. When we divide it out here, we'll end up with 0.858. The units are grams per cubic centimeter. Once again, the number goes with the grams part. The cubic centimeter is basically 1, and they don't cancel out, obviously, in this case. In terms of significant figures, I got 3 there, right? It got me 3 there, so I probably should have 3 significant figures there as well. Yeah. Any questions on that one there? So as I mentioned, there's really kind of a few different ways that you can get a volume. And as I mentioned, just simply if you're doing a liquid, you can fill it up in a graduated cylinder, read the meniscus, and take the reading. If you're doing some type of solid like that block that you did, you could use a ruler and do some measurements. The third very common way to get the volume of an object is also like what you did last. Well, under some water and you threw a stopper in there and you read it before and after that you did it. And that's volume by displacement. Volume by displacement means that if you put a solid object into something like water or liquid, it will basically just is equal to its own volume. So before she takes a dive in here, we have a certain initial volume of water in the tank. She dives, feet first, hopefully. And when she does, obviously the volume in that tank is going to rise to sort of a final volume. And if we take the difference in the water level, and if I could draw straight lines, that difference between where it started and where it did end, that would basically be the volume of the object, or her volume in this particular example. And that's a very common way to find a volume of a solid object. This is just simply send it for a swim in some water, take an initial reading before you do that, take a final reading after you do that. And again, the difference in the volume will give you the volume of that particular object. Hopefully, again, those are stairs, not just markings, so she could crawl out, or she could hold her breath for a long time. We'll hope for the best. We'll see her next semester and see how she did. All right. Hopefully you won't see her next semester. I'll see her next semester. Let's take a look at this one here. A filtered cylinder to 25 milliliters of liquid. She then drops a solid in it. It goes to 33.9 milliliters. The solid has a mass of 63.5. What is the density here? So take a few minutes, see what you come up. Yeah, let's take a look. So again, this is sort of what we were just describing. We got basically a terribly drawn graduated cylinder here that's starting with 25 milliliters of water in it. We're going to take that solid that has a mass of 63.5 grams, and we're going to drop it in. When it does so, once again, we should see the volume level there rise to our final volume here of 33.9 milliliters with our solid in there. It's our initial volume. So the first thing that we really want to think about is the volume here, so that we can go into our density equation. We do have the mass good to go right now. So our volume would be our final volume minus our initial volume. And that's going to give us 33.9 milliliters minus 25 milliliters. Going to give us 8.9 milliliters, I believe. Now we have the volume. We can actually calculate the density of our object by taking 63.5 grams divided by 8.9 milliliters. And that is going to give us 7.1 grams per milliliter as our final answer here. Any questions on the calculation? I ended with two significant figures because of why? It really does go back to this, right? We are subtracting, which means we actually should be looking at decimal places. That's 1 decimal place, 1 decimal place, which means our answer should go to 1 decimal place. But that answer with 1 decimal place still has two significant figures, right? Which is important because the last thing that we did was divide, which means we should now look at significant figures. And this has 3 significant figures. This has 2 significant figures. That means my answers should end up with 2 significant figures. Any questions about there? All right, so here again is density of some common object. As I mentioned before there, liquid water actually is 1 gram per milliliter, which is a common value that you use. I think we talked about it last time, but again, water is an unusual substance in the fact that its solid version is actually less dense than its liquid version, as we might have talked about. And that again is because when water molecules come together in the solid state, they actually can't get very close to one another, and it creates a lot of open volume between the different water molecules. So once again, if we just think about that density equation, because in ice we have a much greater volume than we would say in a liquid state where they could actually get closer to each other and not so spread out. We actually end up with a smaller volume for ice than it is for liquid water. And that's an unusual characteristic of a substance. Most of the time, it is the solid version that is more dense than the liquid version as well. So everything here is going to sink in water, right? Everything here is going to float in water. Here's some other density values as well. By the way, if I take a Diet Coke can and a regular Coke can, and I put it into a sink of water or a big body of water, what will happen to those? Will they sink? Will they float? Well, the answer is one will do this, and one will do this. Yeah. One will sink and one will float. Which one will sink? It's a good party trick, by the way. It is Coke. Yeah. Because Coke has what in it? Sugar. Yeah. Makes it more dense. So the regular Coke will sink. The Diet Coke has artificial sweetener, right? Not as dense. And it actually will float. Like I said, good party trick, just in case you need a trick to do. That does happen. All right, so let's take a look at one last example here. A student needs 150 cubic centimeters of salt for an experiment. The density of salt is 2.16 grams per cubic centimeter. How many 1 pound boxes of salt do they need to buy? This is one of those conversions you do need to know. 1 pound is exactly 453.6 grams. All right, take a moment or two, see what you come up with here. Look, so obviously we're dealing with density, mass, so divided by volume. We do have a volume, which is what the 150 cubic centimeters is. We also have the density given to us, which is 2.16 grams per cubic centimeter. Now, you can use density like a conversion factor and sort of do some problems with dimensional analysis, which means you could, if you needed to, flip the density around and kind of use the centimeters cube up on top and the grams on the bottom if you had to do, some type of dimensional analysis sort of approach to this. If you're not sure where you should start, you have density given to you, you have volume given to you. I'm just going to go out on a limb and say mass seems like a good thing to maybe solve for in this case. We're going to multiply the volume to the other side, going to give us volume times density. I'm actually going to do more of a dimensional analysis sort of calculation here. We would take our 150 cubic centimeters, which is our volume. Once again, we'd just go opposite, so you don't even have to worry about, by the way, rearranging this correctly if you take a more dimensional analysis approach, because all you have to remember is opposites cancel, right? So I'm just going to put my opposites in the right location. And now this should remind you of what you should be doing, which is multiplying. So dimensional analysis can be very helpful in the sense of you might not even have to kind of rearrange an equation per se. You just got to think about what units you got to get rid of and what you got to end with, and it will help you kind of do the math part correctly. So we're going to do that and end up with 150 times 2.16. Going to get you 324 grams as the cubic centimeters would cancel. In this case, if I were going to put an answer here for grams, that is 3 significant figures, right? That is 2 significant figures, as that 0 is not significant because there's no decimal, which means if we were going to give sort of an answer here in terms of how many grams we needed, it would be in like 320 grams in this particular case. We also want to make sure, though, that we do answer the actual question that's being asked, which is the question is how many 1 pound boxes do they need to buy, which means you should have plenty with 1 box, right? So this brings up a couple of important points. Make sure you do answer the question that's actually being asked, right? Which is, in this case, how many boxes do you buy? 1 box will do. You'll have some left over. And again, we still want to keep track of our sort of significant figures along the way. Any questions on any of that there? Comment. So that should wrap up chapter 2, I believe.